Okay, I think we can start. So yeah, I will try to quickly go through what happened with Constantinople. My name is Tomasz Drwięga. I work for Parity Technologies. I'm maintaining the Parity Ethereum client and also working on Substrate project. Yeah, so let me tell you what happened with Constantinople overnight. So what is Constantinople in the first place? So Constantinople is an Ethereum hard fork that was planned for today. Actually, it's it originates from another hard fork that is called Metropolis that was supposed to be launched like a year and a half ago, I think. But Metropolis was decided to be too difficult. Like there was too many features that core developers of Ethereum wanted to push in that hard fork that it got delayed and delayed. So we have decided to split it into two hard forks. The first one was called Byzantium and actually launched last year. And the second part of this hard fork was supposed to be called Constantinople. And actually, it also got a little bit contentious, and there wasn't that many features as we expected in Constantinople. So everyone was hoping for proof of stake and account abstraction and other features like this. But at the end, there was no time to discuss everything, so it became a smaller hard fork. Actually, everyone thought that it's going to be just like regular technical hard fork without any issues, and it will just pass smoothly. So here is a list of features that was supposed to be activated during Constantinople. First, we have something that is called difficulty bomb diffusal and reward reduction. So this is the only like contentious, like community contentious EIP, I would say. Especially the second part of it. So first one is because in Ethereum there is a thing called Ice Age, which is an exponential increase of block difficulty built into the protocol. So if this starts to kick in, blocks are being produced slower and slower until it just stops, like the network stops. The reasoning for this is this was supposed to be push for developers to actually switch to proof of stake. So the idea was, yeah, we don't want to be on proof of work all the time. In 2 years since launch, we want to have proof of stake. So this will never happen. Like we're never gonna get to this Ice Age. So block time will stay 15 seconds. But to have this additional push to switch to proof of stake, we have put this difficulty bomb there, and actually we had to diffuse it a couple of times already. So maybe it's not diffused, but it's just pushed back. So we like add 1 year, one more year to switch to proof of stake. And the second issue was the block reward reduction. So it happened already in Byzantium, and it was supposed to be reduced even more in Constantinople to 2 ETH per block. Yeah, but anyway. Then the rest was supposed to be the technical details, I would say. So first we have EIP 145, which is bitwise shifting. And this is just like 2 or 3 opcodes that allow you to take a number and shift it to left or right with rounding or not. So this is something that people thought should be there. It's easier to, for instance, calculate some signatures or verify some signatures in smart contracts if we have those opcodes in EVM. And everyone just thought, yeah, this is something that was supposed to be there since the very start, but it just, like someone missed it. Next thing is 1052, which is X code hash. This is also additional opcode available for the EVM. And there is an opcode that is called code hash, Xcode, that just gives you the code of another contract on the EVM. But this is quite expensive because contracts can be quite big. So the reasoning for this was like sometimes it's just fine to have the hash of the code, which should be much cheaper. And then you can verify, yeah, that contract is the contract that I want to interact with because it has the matching code, for instance. So this is also like really tiny feature that was supposed to be added. This one is a little bit more interesting, and I will show it on the next slide. And this one is falls more into this category. So like simple feature, but it's a little bit different than the other ones. So all of these, oh damn it. Okay, sorry. Yeah. All of these ones here, they are just adding new opcodes. This one is different. This one is modifying an existing opcode. And I will get into this difference in a second. So first, create to. We already have an opcode that allows you to create a new contract in Ethereum. It's called create. Like this one, someone wasn't very innovative in terms of name, so they just called it create to. So it's a different kind of contract creation. So if we are creating contract currently, the address of the contract we will get is over here. So we take the sender, so the person who wants to create the contract. It can be either created via transaction or through another contract. And we take something that is called nonce, which is just like a number of transactions that were sent from that particular account in the past. We hash this to take the last 20 bytes, and this is where your contract will live in. So the destination where your contract will be deployed. Why it's calculated this way? It doesn't have to be calculated that way. It doesn't really matter. The point is that we want to have some random address that this contract will live in, but it has to be deterministic because everyone will need to have the same way of computing that contract. And also, it would be nice if it didn't repeat the same address for the same sender. So you can send as many transactions as you can create as many contracts as you want. Yes, it's like internally. Whenever you are creating a contract, then you are creating incrementing the nonce. Yeah. So this is how we create contracts right now, and this new create tool is a little bit more interesting because it doesn't matter. So here, the only thing that we use to compute the address is who is sending that contract and like which contract number is it. Here, the address actually doesn't depend on when you create the contract, but rather what the contract is. So to compute the address, we take the initial code of the contract. We take some salt that can be provided by you. We take the sender, and then this is the address that your contract will be deployed. Okay. So what are the consequences of this? First, we have this. Let me go back here. Yeah. First, we have this predictable addresses. So this is something that people are excited about. So if you have a code of the contract and you know who's gonna send it and what's the salt, you're gonna know where this contract is living. So what you can do is you can send funds to an empty account because you know that there's gonna be a contract there in the future. And if you want to, if the person that you send the money to wants to reclaim those funds, they just need to deploy that contract and get it back. Actually, they could do that with regular create as well, but there is only one opportunity to do that, because if you skip the nonce, which is something that you don't control, then you lost your funds because you won't get the same address never ever. With create2, it doesn't matter where you when you deploy the contract. It just matters like what the contract is. So you can agree, yeah, I'm gonna receive the funds on that particular contract, but it's not yet deployed. But don't worry, you can send the funds already, and then I will deploy it later in the future. So it's important for layer 2 solutions, things like state channels, but yeah, it's details. Okay. One more very interesting consequence, and actually, if you would have asked me like where do I see a highest possibility of a bug being introduced in this hard fork, I would say that create2 would be a culprit. So this is something that we realized a little bit later, that with create2 you can actually create a contract, then you can suicide the contract, so you can kill the contract, that the contract is no longer there, but then you can resurrect that contract under that particular same address. And what's even more interesting is that this resurrected contract can have a completely different code. How, you might ask? Because, to compute the address, we actually use the initialization code here. So if the initialization code has to be the same, right? Yeah, question? No. So if you recreate the contract, it's gonna have empty storage. So the storage is yeah. So if you create this contract again, it's going to have fresh storage, so you can have completely different storage layout. And also the code can change, because this init code is actually what you do in constructor. And what you can do in constructor, you can actually fetch the code from a different contract and say, okay, I want my code to be actually this. So the initialization code is the same, because say, okay, take the code of a contract somewhere else, or take the code that is returned by a function of that other contract, but you can change this thing that the other contract returns. So this is something that, like, the create2 was introduced in EVM to get this predictable addresses for layer 2 solutions. But this was kind of like unexpected consequence that people didn't really analyze. That like, are we breaking some assumptions? If you suicide a contract, currently it cannot be revived. With this, it can be revived. What can even have a completely different code. So I was expecting that if there are dragons, they're gonna be like somewhere here. But actually, this is not what happened. And this second feature, yeah. Correct. Yeah. Yes, but yes, unfortunately, yes. Yeah, so that's correct. If you have used create to create a contract, then you will never get the same address with create2. And also, as Krzysiek said, if you are interacting with a contract that was created through create2, make sure that you have the latest state, because if you see like how this contract looked like 1,000 blocks ago, it might be completely different contract currently. Yeah. So yes. So if you generate the same address, like this is part of the spec here for create2, that if you get the same address, then the create tool will fail. Okay, yeah, so the next feature that is like non-trivial, so let's say the other ones were really trivial, like adding some opcodes, changing the block reward. The first one interesting was create to, and this is where I expected bugs. The second one is a little bit more specific. So the idea here is there is an opcode called store, which allows you to modify storage. So this is this persistent storage that your contracts can use. So if you want to call a contract, it can remember something until the next transaction. And store was pretty complicated already, because the idea is that when you try to read a storage entry that is not set, you're gonna get 0. Okay, so the storage, the key for the storage is actually a number, 256 bits number, and all the storage is initialized with 0, so you can query any storage you want, and you're gonna get 0. Then, if you want to set a storage entry to something that is not 0, you have to pay gas, and the base gas for this was 20K gas. So if you change this storage from non-existent, so being 0, to existent with some value, you have to pay 20K. Then if you keep modifying that storage, which we have here, so if you change it from X to Y, let's say, and Y is not 0, then you're just gonna pay 5K, okay? So I'm changing from 0 to 3, then I'm paying 20K, then from 3 to 5, 5K. The reasoning behind it is if it's set to 0, we actually don't need to store anything, because 0 is, just nothing, so it's initialized 0 by default. If it's set to something, the Ethereum state needs to grow a little bit, so you have to pay for extending the Ethereum state. If you modify it, you actually pay something, but not as much as creating the state, because you are not growing the state, you are just changing the state. And then this one here is much more interesting. If you reset storage entry to 0, so you delete the storage entry, you pay 5K, but you actually get 15K back at the end of the transaction. So this is something that is called gas refund, and maybe you have heard of a project called Gas Token, and their idea was, okay, if gas is cheap, we can actually initialize a lot of storage entries to non-zero, and then when gas gets expensive, so you have to pay a lot for the transaction, you can actually reclaim your cheap gas that you initialized earlier. It's a pretty cool idea. The issue is that the reasoning behind those costs is we want to keep Ethereum state not growing that fast. So if it grows fast, then it's an issue for the clients, because you have to sync a lot and it uses much more disk space. So if you clear an entry, it means that you are shrinking the state. We are giving you some money back. So this is how it works currently. But even though you only pay 5K, a lot of layer 2 solutions said, okay, it's still too expensive. Sometimes I want to change the storage value in one transaction twice. So I'm not really, so with current S-Store, you're gonna pay 10K, right? Because you change it to Y and then to Z. And the reasoning behind costs were it's pretty expensive because we need to write something to disk. Okay, so as Krzysiek mentioned, EVM gas calculation is pretty complex, because the idea is that we need to, when we are executing a contract, we need to cater for different things that we actually do on the machine. So for instance, if you are adding two numbers. This is something that can be done completely in memory, and it just uses a couple of CPU cycles. But if you want to write something on the, into the storage, it means we have to go to disk. And going to disk is, like 100 or 1,000 times slower than doing anything in memory. So the gas costs should actually be higher for this. If you change the storage entry twice in the same transaction, we actually don't need to go to disk because we have a local cache, and we only write to disk after the transaction is executed. And this cost here, like paying 5K for every modification, was not reflecting the actual costs that the contract is doing on the machine. Is it remotely clear? Okay. So because we didn't have to go to disk, the idea was, okay, let's allow people to change the storage within the same transaction context in a much cheaper way, because we actually don't write anything to disk. We can just do it in memory. So this is an optimization that all the clients were doing anyway, and the change was just to reflect that optimization in the costs of that instruction. So this stays the same, this stays the same, this is the same, but if you go in the same transaction, if you change from Y to Z, you're only gonna pay 200 gas, okay? And if you change it back to the value that was initially, then you're actually gonna get a refund. Okay, yeah, this is why. So as I said, temporary changes, so only within transaction contexts were believed to be too costly. It doesn't reflect the actual cost because we don't have to go to disk, we can do it in memory. And yeah, I mean, it doesn't seem too complicated, right? It's just, yeah, let's just reflect the costs of what the client is actually doing. And what went wrong? So this went wrong. This is a blog post that was released yesterday, and they say, Constantinople enables new re-entrancy attack. I'm gonna go through details on the next slide, but let me just mention that there was plenty of time to release that, and like surprisingly, it went out yesterday. This is some kind of like smart contract security company. That's really cool that they found it. That's a little bit unfortunate that they found it a day before release. So yeah, let me explain what the re-entrancy attack with Constantinople is. So first, what's the re-entrancy attack? So this is like pseudo solidity code. I think it doesn't compile. I was just writing it yesterday. What you can do is imagine you have a contract that you have deposited some funds. It has a storage variable saying, yeah, this is how much funds you have. Let's imagine that this contract is actually used by multiple people. Okay, so every person has a deposit variable, and it means that even though I have deposited 1 ether to this contract, the contract actually store like 10 ethers, right? And I can withdraw from that contract at any point, and what this contract is doing, it's checking that I have anything deposited. I should have like 1 ether there. Then it's doing, yeah, I want to transfer that deposit to you. So the contract A means my withdrawal address. And after I transfer that, I want to set this deposit to 0, right? So you don't have any more deposit because I just transferred it to you. So doing a transfer is actually calling a default function in a contract, which is written by this in Solidity. And what I can do in my contract, because the destination of the withdrawal doesn't necessarily have to be a regular account, it can be another contract, right? So what I can do is I can have some flag that says, oh, I've been called or not. And if you call me for the first time, I can actually call withdraw for the second time. Does it make sense? So what we do is within the same transaction stack frame, we are trying to withdraw. It goes to my contract that receives the money, and then this contract calls withdraw again. And what the contract is doing is checking, oh, you still have the deposit, because I'm in the middle of transferring that deposit, but you still have some. So it transfers me once more the same value. Then I say, okay, I'm done, right? And only after it sets this to 0. Does it make sense? I'm going to get the same transfer twice, even though I should only get it once. So this is something that is called reentrancy. This is not how the attack vector that they described work. This is something that DAO was susceptible to. Anyone remembers DAO? So an attacker was able to drain money from the DAO using like a very similar method to this. And this is like, let me just say, this is strictly an anti-pattern in Solidity to do something like that. What you should actually do is to set deposit to 0 before you do transfers. So it's, what's the pattern called? Like, no, so that's the different thing, but when you are writing a Solidity code, you should have like requirements, then state modifying, and then effects, or never mind. But if you are doing a transfer, or if you are calling an external contract, you should do it at the very bottom of your function. So you need to do all the accounting before you actually do the transfer to a second person. Yeah, and then how this reentrancy, so reentrancy is something that can be done on the Ethereum main chain like today, right? But we want to protect ourselves from writing contracts like that. And also after the DAO, Solidity has actually created, so if you are doing this, you need to transfer some gas for the receiving contract to do something, right? So this wouldn't work actually, because transfer function in Solidity just gives you like 21K gas. So it's not really enough to do another call to a second contract. The DAO was not using transfer function, it was using call, which was transferring the entire gas that was available for that function to this function, so then you can call again. But even though we have transfer now, and we don't transfer like large amounts of gas, the minimal gas that you can transfer with a call is actually defined as something that is called call stipend. And it's 2,300 gas. So this is a limitation, not one coming from Solidity, but one coming from the underlying EVM. And the idea behind it was that when you are doing a call and you are transferring some money, a call recipient can't modify the storage, but can just emit an event and can, you know, tell the world that it received the funds. And when this call stipend was defined, everything was, because it was 2,300. So it's much less than any storage operation required. But with Constantinople, it was supposed to be changed. So they figure out that with this call stipend, you can actually modify storage now, because it's going to be just 200 gas if you do it for the second time in the same transaction. So they came up with a really weird contract that sort of shows how you can exploit that thing. Yeah, so we have a contract that is called payment sharer. the idea is that two people can get into that contract, and then they can say that they want to split funds that they both own within some, within some, like by some value. So for instance, I'm entering into this contract with another person, and I'm saying that I'm gonna get like 70% of the money, and the second person is going to get 30% of the money. And this particular contract has to be used by multiple people. So even though we own only like 1 ether on that contract, it still holds a little bit more. So let's say 10 ethers. And what we do is, whenever we are ready to withdraw our funds, we call this split funds method. It's simplified here because the idea is that we should check the signatures that we actually both agree to a particular split, and we want this money to be distributed that way. And what we do is we take the first address, then we take the second address, then we take how much deposit we have, then we remember about re-entrance. We know our accounting before actually doing a transfer. So we say deposits ID equals 0, right? And then we do 2 transfers. So first one is going to be transfer deposit multiplied by the split divided by 100, right? So transfer, let's say, 30% to this guy. And the second transfer is transfer the rest, so let's say 70% to this other guy, B. Does it make sense? Okay. And the attacker contract, so what the attacker can do is it can use this contract and register first and second addresses to something that he owns. One of those addresses, actually the first one, has to be this particular attacker contract. And how this attacker contract work? So what attacker is doing is calling this attack function, and then it updates the split. So we need to call this update split function here, and then we want to split the funds, okay? So here this 100 means that the first guy will get everything, and the second guy should get 0, right? Calling split funds actually goes to here. So we take first, we take second, we take deposits, right? We do this. Then we transfer 100% of the deposit to contract A, be the same contract here. And we're going to call the default function in that contract. So what happens here? This is basically calling the update split function and changing the split to be 0 instead of 100. Okay? We can do it because we have enough money for the call, enough gas for the call, and also modifying this storage entry here is actually cheap now because we have modified it here for the first time. Does it make any sense? So we have paid 5K here, but now if we modify it for a second time, we're going to just pay 200. And what happens is that it allows us to change the split in the middle of this execution here. So split's ID was first 100%, so we transferred 100% of the deposit to A. Then we changed the split to 0, which means that this second transfer will actually transfer 100% of the deposit to this. Okay. Yeah. So that's the attack that they came up with, and yeah, it's pretty complex, and okay, and actually. Yes, exactly. So yeah, the idea is that the attacker is actually both A and B. So he controls both of the addresses. So it's a really specific contract. Like you have to access the storage here again. If you would just like assign it to a variable here, it would work correctly because you read the storage once. So it's a really specific contract and a really specific situation that they came up with. But the cool thing that they did is they actually attempted to analyze all the contracts on blockchain to figure out if there are any that could be susceptible to this particular attack. And this was actually possible thanks to a Polish guy called Tomasz Drwięga. I don't know if you guys know it. He has a pretty cool, he was like hacking on a pretty cool platform that allows you to like analyze the contracts symbolically, and together with BigQuery from Google, the entire Ethereum blockchain being available for analysis on the Google platform, they were able to do it like really fast, much faster than the regular way the Ethereum Foundation are analyzing blockchain. And I think they actually found one contract that was used like once 2 or 3 years ago, and they found that there is one that is susceptible to this attack. But even though just the knowledge that we might break something was enough to call for pulling the hard fork off. So the hard fork was actually postponed, so it didn't happen today. What was happening yesterday was both the Geth team and the Parity team, like there was a call with all the stakeholders, and they figure out that, yeah, we need to cancel the hard fork. And the best way to cancel the hard fork is to ask everyone to update to a newer version of the client that doesn't have the hard fork block in. So what we were doing yesterday, we were actually, the hard fork was just pulled off like 35 hours before the actual due date, and both clients were doing like late night yesterday to actually cancel the hard fork. So yeah, this is what I was doing yesterday. Cool, and that would be it. So Constantinople didn't happen. Any questions? Mm-hmm. Sure. Yeah, so the only thing that it's doing is actually calling the update split. So when you transfer the funds, in the middle of the execution, we update the split from being 100 to being 0 here. Probably just to fit into this 21K gas limit. But I wasn't analyzing it closely. But I would suspect that, handwritten assembly can be optimized enough, because it's like calling this function and modifying this storage is just enough. So it wouldn't be possible with the regular 5K cost because the gas stipend was not enough, but because it just costed 200. Due to this change here, so we have updated the same storage entry earlier in the same transaction frame. So this was the cheap change. I'm not sure. I don't remember. But I think it was like ERC20 contract, so it shouldn't really have any funds. Like possibly it had some tokens, but yeah, I don't know what tokens. I'm not sure either, but I think like this decompiler is. It allows you to query the contracts somehow. Yeah, so I think they use a particular query that is able to detect a transfer followed by a storage read, and yeah, something like this. Because like they obviously cannot find contracts like that on a blockchain because this is the exploit, but they need to look for contracts where after doing a transfer, you actually do another transfer, and in between you actually do a storage read. So that should be something that you can easily find. You mean for the future of Constantinople or future of hard forks? I don't know. So like all the features that we had in this hard fork, so this is still something that we want to include in Ethereum. It's just matter of like how do we resolve the issue that arises here. Do we actually need a solution? It's just like we just need more time to discuss it. Maybe it's gonna go in the same way. I don't think so. I think they're gonna change something so that we don't have a way this kind of attack. But all those features are gonna be in the next hard fork for sure. Indefinitely. So we just like disabled the hard fork, but we didn't really decide on the next block number. Mm-hmm. I don't know. I haven't analyzed it yet. Like people start to say that we should have a static call transfer or something like that. That's a special call that you only use if you want to transfer funds, because we already have static call, which allows you to query a contract, but we don't have a way to transfer value without actually allowing the recipient to do any modifications. Yeah, maybe like I also heard some discussions that people think that gas stipend is a completely stupid idea, and it shouldn't be there in the first place. Like if you want the recipients to actually generate the log, then just pass it the gas. It shouldn't be provided as is. Like some other solutions that people were showing is we do actually have a way to transfer Ether to a contract or to any address without calling even the default function. And it's a way you have to create a contract that self-destructs to some other address. And I was also talking with some guys during DEF CON, and they say, like, this is how we do payouts, because that's the only reasonable way to transfer funds. You don't have to care if there is, you know, if someone wants to receive it, if there is a contract there, how much gas you provide, and any re-entrancy bullshit. You just send the funds. But I think it's not really the way we want to go with Ethereum, because that would make Ether even more special than it is right now, and the trend is rather to have Ether as a ERC20 token, so it's not special in any way, and remove this special notion of, you know, value transfers. It should be just transferring tokens. Yeah. So I don't know yet. I think it wasn't intentional. I think it was just coincidence, and they wanted to, you know, tell community about it. I think they actually contacted Ethereum Foundation a little bit earlier, and they told them about the issue, but it was just maybe like hours earlier, not days earlier. So they made it public like right away. Yes. Mm-hmm. Yeah, yeah. But I mean, I think like the learnings from what happened is that Ethereum, even though it has like a lot of governance problems, if you follow the space closely, and we can't really decide on many things, it's sort of like Poland. Whenever there is like a real threat, we can unite and we can pull the hard fork off in 35 hours. So I think it's maybe a good thing, maybe not, but yeah, interesting thing to see. Okay, cool. Thank you.